I was about to give up, but then I switched the wires over and I put negative polarity on the emitting points, and I threw the on switch on the CRT, and the thing floated up near the ceiling.
Hello everyone, and thank you for tuning into a video that's going to be rather different from what I've done before. Last year in April, I did a mission where I orbited Kerbin using only ion engines. This turned out to be my most popular video ever. It did well in not only the KSP community, but outside of it as well. What I take from this is that there's a lot of interest in ion-powered flight. In that video, I mentioned that there had recently been a flight from a team at MIT of a real-life, fully self-contained, fixed-wing, ion-propelled plane. I was a little bit remiss in my research at the time because I thought that this was the first flight of a self-contained ion-propelled craft in general. It turns out that this first flight actually predates the flight of the MIT team by about a decade. My guest is Ethan Krauss. Ethan is an electrical engineer from Ohio, and he is the inventor of the first self-contained ion-propelled aircraft. Ethan was kind enough to have a conversation with me about the history and technical details of ion-propelled flight. Break that down for us. What exactly is meant by self-contained ion-propelled aircraft?
Since 1950, there have been inventors that have made devices that can either swing around a pole or float up into the air with a very large external power supply, a high voltage power supply. But they were never really, they were just a curiosity, like a science demonstration. And the problem was, most people thought you could just never get that power supply on board the vehicle. If it takes a 200-pound power supply to lift a small toy, it just didn't seem like it was going to happen. And I worked on it for years and years and kept making smaller power supplies and better ion-powered aircrafts.
I found pictures on your site of experiments you were doing. I think I saw some as early as 2002. So
sure.
You've been working on this for a while.
20 years, yeah.
Do you have an idea of about how many different iterations or versions or tests you've gone through in that time?
People might almost be worried about me how many I've done, It's like bags and bags full. I used to, on the early experiments, I had paper bags that were, partially filled with burned out transistors. And I just did, it was kind of like reckless experiments in the very beginning. And then I became more careful and guided about it and used more math. Still, I have a lot of experiments that don't result in a great deal of improvement. And so I just do a lot of experiments,
Yeah, you can't really know if something's going to be an improvement or detriment or just neutral until you try it.
Somebody told Edison they had a great idea, and he said, "Well, just go do it."
Yeah, like I know in Kerbal Space Program, this is the program the process we go through. But in real life, there's so many more variables to deal with. There's so many more things that could go wrong.
Yeah, it gets to the point where you want to glue something together, but the glue keeps failing, or it's too heavy, or you put the glue on, when you remove it, there's like a glue thread, and that can be a problem. So you end up doing this like research project just to get the right bottle of glue, and it can take weeks or months to get the glue just right.
What is the best glue?
Well, I'll tell you, each part of the thing has a different kind of glue.
So you've optimized this to the point of using the exact optimal glue for each part of it.
Exact right amount and exact optimal glue for each part. Almost. It still has room for improvement, but
right.
Everything, every little piece of material on it takes a lot of thought, and you learn the hard way, kind of.
Many of my viewers probably have a pretty good idea of the general level of how an ion engine works, but I think almost everyone could benefit from hearing a more detailed description of how exactly the engine you're using works.
All these sorts of propulsion systems, in-air ones, use a emitter surface and a collector surface. And the emitter surface is made of very small points or very thin wires. And the collector surface is made of rounded conductor. So when you put a high voltage DC between the two surfaces, there's an airflow from the sharper surface to the more rounded surface, right? And in the case of the vehicle that I have, you can't actually see the emitter wires on the videos. What you're seeing are the emitter wire support, horizontal emitter wire supports.
Gotcha. Okay.
So emitter wires mine are so thin that you have to wear mag goggles to see them. You know?
So what are the thin wire-looking things I see sticking up?
Okay, those are very thin plastic tubes, and they support their special dimensions and material, and they support the emitter wire that looks like a cobweb going around above it.
Right.
Those are just supports for that.
Right. So that's just part of the structure that's holding everything together. Ionocraft are solid state. They have no moving parts. Explain to us how that's possible and what advantages this offers. What's
the advantage of a transistor? Well, there's a lot of advantages, as we know. We wouldn't be on the computer today, The way that it flies with no moving parts is that it does have ions that move, but it's mostly electrostatic pull. People often think that you have this corona wire that kind of sizzles and glows and heats the air and rips particles loose and so on. And if you don't do it right, that's kind of what is happening. But if you do it right, you have this thing that's almost silent, and it just releases electrons, and the O2 molecules absorb those electrons pretty silently. Since the collector surface is at the opposite polarity, O2 molecules with extra electrons jump down to that positive surface below. There's an analogy with pool balls. You get some of them moving in one direction, and they knock the rest of the pool balls along with them. But actually having the other pool balls in the way probably reduces the force involved.
Although if you're moving more mass,
you're
getting more force from that too.
You could either move the mass faster, or you could move more of it more slowly.
Find the amount of mass moved, and then the mean velocity that you've moved it at, and then you got your force.
Yeah, and how much?
This has got to be hard to measure, though. I guess you could look at the final resultant force, and that's the real measure of if you're improving.
The first 6 years, no, not 6 years, 11 years that I did this, devices were hanging under a postal scale. And I would test, and I would see, oh, gee, I'm getting, 10%, 20, 30% lift, and I would just keep playing with everything until the numbers got better, until the scale would read less and less. And that way I didn't have to, have the thing, have landing gear on it or any of that extra weight, That's how you measure how much force you're getting, how much thrust to weight ratio, right? One of the first times I flew it with legs, I have a video of that published on my site, on my YouTube site. And
which I will link in the comments to this video.
And that one, is one of the first ones where it had legs and tie downs instead of a postal scale over it. And it was kind of cool to see it take off with nothing over it,
Right.
And then people were saying, oh, but it's got tie downs. And before that, I could just fly it with, one safety tether, going
right.
to the postal scale. So, and you could see the thread get all loose, and the postal scale go up to 0.
In Kerbal Space Program, the engine that we have available to play around with in the simulator is based on the engine in the Dawn spacecraft. But they've actually, by several orders of magnitude, they've increased the thrust, presumably for like the pacing of things, so things don't take as long. I don't think your average hobbyist Kerbal Space Program player wants to wait 3 months to do a mission. The stats that we've got to play with are, we have a 250 kilogram engine, and it gives us 2 kilonewtons of thrust.
Okay.
Which is several orders of magnitude more than what the Dawn spacecraft had. It has 4,200 seconds of specific impulse, which is also about a third more than what the Dawn spacecraft had. What's interesting about those numbers is that means that if you just have the engine in standard gravity, the engine does not have enough thrust to overcome gravity.
Yeah.
Just by the engine. But what you've achieved in real life, more thrust than mass by quite a bit, because you have everything else that's in this on top of the engine. Yeah. So clearly, while these engines are similar, what you're doing is different. So Like, what's different in the structure of what you're doing compared to a Hall effect engine?
The structure of mine, it does have a large surface area, especially large surface area for its weight. And it has very long collector emitter surface. I mean, it's got 8 rings, and the outer diameter is 50.5 inches. And so these 8 rings, if you put them all together end to end and straighten them all out, it would be about 60 feet long of collector. And maybe it doesn't sound very scientific to use empirical.
Yeah, we're very metric over here, but we're also good at converting from imperial, so I think we'll be all right.
20 meters, okay. So yeah, it's like 20 meters of collector surface, and that weighs just a few grams. The actual aluminized plastic weighs 2 grams, 2-3 grams with the glue and all. And then you got a structure to support all that material because it's very lightweight. It just all kind of adds up faster than you would expect too when you're building it in real life. Anything you put on there, you have to take into account how many milligrams you're adding. So, but structurally, the emitter wires on this are 6 inches high on this one. The lifters have usually, 2 centimeters high. So 6 inches is, I have to figure out how many centimeters, 2.54.
Right, so that's about 15 centimeters.
And that's more efficient if the structure is light enough, and if you use thin enough, crazy thin emitter wire, and if you have a low current power supply, it all works as a system. It's like a computer. If you put the wrong value capacitor in there, the whole thing probably won't work. Wrong value resistor, right? So,
and, what I've noticed in some of the missions I've done in the simulator is when you're really trying to optimize, you reach the point where things that seem really minor become really important. I'll be building something that's 100 metric tons, and it'll get to the point where I'm looking where I can shave off just tiny fractions of a ton and just 10 kilograms here or 10 kilograms there, and it starts becoming a significant improvement that you get excited about. So yes. I imagine you're at the point where even something really insignificant, like every milligram, I imagine really has to count.
I made a microgram scale with this real long metal rod, and it bounces on a razor blade. And I built it so that I could measure the weight of the drops of glue I was adding. Right? And so if you're adding thousands of drops of glue, and each one weighs a milligram, it can add up, And so you add all that up, and that would seem, insignificant. Who cares? Just slosh a little glue on here and there. What's the big deal? But it all adds up, so you have to be careful. And the emitter wires that are 2.5 microns, people figure, well, this is thin wire. This is 5 thousandths of an inch. That's like looks like a hair. It's probably just fine, right? But it's not. It's those microns make a big difference.
What are you looking at next for optimization? Is there more weight savings in there, or better power supply, or
everything? Every part of it is getting better. It's a big chain of components, and they're all improving. I mean,